now turn to Philippe Rigollet, who is our third speaker, no, fourth speaker.
All right. I don't know if this, yeah, okay. So I'm going to stay at the podium because I don't have a clicker. So I'd like to talk today about a problem which I've been working on with two very bright young people, Nicolas Flammarion from École Normale Supérieure and Cheng Mao from MIT. And this is a problem where we've been trying to gain some insight about some computational problems using statistical models. So there's been a trend recently in statistics and machine learning that consisted in trying to formulate some average case models for problems that are notoriously hard, and we were actually able to solve them and explain why in practice those problems would be solvable and why you would sometimes run into hallways and people would tell you I solve LP hard problems every day. So the problem that I'm interested in here is probably at the frontier of what we understand from a computational point of view. It's a problem involving permutation. So let me start with a simple example. So there's a notion which is called C1P, which is either the consecutive one property or the consecutive one problems, depending on if you're a positive or negative person. And the problem is the following. I give you an n by n matrix with 0 on entries. So 1 entries, and in general throughout this talk, entries in red are going to be highly positive and entries in white are going to be zeros in general. Okay, and so this matrix has the ones that appear consecutively in each column, right? So they're contiguous regions of ones, and so that's a matrix that has the consecutive one property. And so the problem associated to this is if I give you a permutation of the rows, and I promise to you that this matrix is going to be such a matrix, can you actually recover the permutation that gives you this property? All right, so why would I care about this problem? So we'll see in a second that I could care just from a computational point of view, but the problem I'm actually interested in is the so-called dating problem. All right, so there's two meanings of datings that are actually represented in this meme, and I'm actually thinking about the second one. So you have some archaeological remains, and your goal is to date them, right? So, so we know, so this is a problem that we know how to do with carbon dating these days, but in the early 20th century, there was a famous archaeologist and Egyptologist, Flinders Petrie, who died just before carbon dating came, and he had this problem. He went to the Nile Valley and he just excavated, I think, about 40 tombs, and he wanted to order them in such a way that he could recover the chronological order of those tombs. And the way he was doing this is by collecting artifacts from each tomb, and his thesis was that artifacts buried around the same time should be similar, right? That tombs that were appearing, so they should, you know, there was a fashion, right? If they were like iPod 3, you would think that they were mostly from the same period than the ones in there. So this, there were no iPod 3, but these are the kind of artifacts that you could find in the tombs there. And so his idea was to say, okay, if I start putting a 1 for each grave that contains a particular vase here, and I start listing all those things, then my goal is to just reorder the graves in such a way that I actually see consecutive ones. And if such a thing happens, then I will actually have an order for the artifacts, which will turn into an order for the graves. And so this order for the graves is the one that satisfies Petrie's thesis. The way Petrie did this was actually built this like wooden matrix and would actually change things, permute the rows of the matrix by hand by taking one and moving it up there. And he had some, of course, heuristics because, as you can imagine, there's quite a bit of permutations involved here. So, of course, carbon dating came, so I'm trying to solve a problem that's now solved by other technology, and so why would I care? And the way I came to this problem is by thinking about de novo genome assembly, so this is basically how it goes. So I give you a string of DNA, and the way I'm going to sequence this is that I'm first going to clone it to account for mistakes that I might be making, right? So just, you know, I think right now it's about 10 to 30 times. Now I'm going to chop it into pieces because sequencers cannot read long pieces of DNA. So you cut it into little pieces, so now I don't see anything on there. I don't know what's written on there. And I'm going to put everything into a sequencer that's going to actually read them and give me what the sequence is on much shorter pieces. Now my goal is to reassemble them. The way it's done in practice is that there's a reference genome, and you take it and you scan it with your little piece, and you say, oh, it should be here. But the grail of this problem is to actually do it de novo with nothing. Just things that are similar should be close. All right, so here's one way we can do it. I'm not saying this is the way you would want to do it in practice, but you would put your reads into a row, and then you would have k-mers. So here it's 3 mers, so little sequences of 3 letters. And then I'm going to put a 1 if this sequence appears in one of the reads and 0 otherwise. And then if I start permuting the rows to yield C1p, I should have something that gives me a notion of ordering, right? There's this underlying one-dimensional manifold that's generated by the DNA. So the title of this talk is not C1p. The title of this talk is seriation. And so how do we go from C1p to seriation? So seriation is a problem which is essentially the same thing. I give you a bunch of points. They know to belong to a one-dimensional manifold, and I'm trying to reorder them. And so what happens if you take a C1p matrix and you form A transpose? So now this is a 3-dimensional visualization of this matrix. So you see high values means high entries, right? Large values for the entry. And you can see that it has this mohawk kind of shape, right? And this is actually characteristic. When it decays as you go away from the diagonal, this is called an R matrix for Robinson. And it turns out that this is not a property that's only valid for C1p matrices. There's other matrices that are interesting that have that. And those are unimodal columns. Unimodal means they go up, each row goes up and then down, just one time, up and down. Unimodal means only one time change in the direction. And this will be useful presumably if you have counts rather than indicators of presence of an artifact, right? Maybe the guy had 15 vases, and so that meant that was really popular. And this is what they have, right? This is actually the original paper by Robinson, and he would say that there's percentages of different types of artifacts that you would see there. So if you don't really do the outer product of A transpose, but if you do something that's similar to it, which is actually strictly equivalent if you have 0-1 matrices, so I'm not going to describe in details, you also get an R matrix. So it's not just as sharp as the mohawk, so I learned from Mancourt that it was a faux hawk. And so it turns out that those two matrices can be dealt with in the same way. So how do you solve this with those matrices? Well, this is actually a pretty old problem. Fulkerson actually looked at it with Gross in 1964. He looked at the C1p problem, and he gave some combinatorial algorithm to test for C1p, followed by a paper that would recover the right permutation from purely combinatorial perspective. Late 20th century, there was this paper by Atkins et al. That said, actually, you can just use spectral method. You look at the left singular vector of your matrix, and the order of the entries actually gives you the right permutation for an R matrix. All right, so the question is, are those methods robust to noise? I'm a statistician, and that's the first question I ask for everything I see. All right, so what we're going to do is we're going to talk about noisy seriation. So I give you, say, a unimodal matrix. I add some noise to it, and then I permute the rows, and I give you this matrix. Okay? So the question is, well, what can you do with it? So let's just recap. So you have a true unknown matrix that looks like this. I first add some noise, and then I permute the rows. And what I'm asking you to do is to recover the original matrix. All right, so your goal is from this matrix to recover that matrix the best possible way, to denoise it.
The A matrix is still 0-1 matrix? Or
No, it's a unimodal matrix. So it doesn't have to be 0-1 now. Think about entries between 0 and 1, like percentages. All right, so now I'm going to have to start using equations. The equation is fairly simple. It says you observe a matrix, which is a permutation applied to the left of an unknown matrix that has some nice structure. For example, all the columns are unimodal. We're going to deal actually mostly with monotone, so they always go up or always go down. And then I add some noise, Z. And I'm going to think of Z as being sub-Gaussian, so that's well-behaved noise. But in particular, it allows for Bernoulli noise, and that leads into some problems related to bipartite rankings that are actually quite interesting. I'm not going to go into the details, but I want to tell you how this actually brings in together two different notions. The first one is, well, every time I say unimodal or monotone, there was this famous book in the early 70s in statistics called the 4 Bs, or 4 authors with last names starting with B, and it's called shape constraint estimation. And this is actually a very well-studied problem. And we know if I give you a vector plus Gaussian noise, and I promise to you that this vector is going to be, say, monotone or unimodal or convex, right, and everything being defined in terms of finite differences, right? So monotone, say, it decreases, unimodal goes up and down, convex has this nice shape. Then if I give you this guy, theta plus some Gaussian noise, then the question is, at what rate can I leverage the structure to denoise this vector? So this is a well-studied problem. Oh, thank you very much. So this is a very well-studied problem, and the question is, for example, if I look at the average squared error that I can make when I estimate this vector, so that's the inf soup. So here it just says the best estimator I can get to uniformly estimate theta. Then the rates are n to the negative 2/3, n to the negative 2/3, and n to the negative 4/5. And you could go beyond that because those are actually pretty standard rates of estimation. If you're familiar with non-parametric estimation, this is this famous n to the negative 2 beta over 2 beta plus 1, where beta is the smoothness of the function. And you can sort of think as these are functions that are well approximated by linear functions or quadratic functions or constant functions, etc. So you could go with like successive differences further on. But let's keep at the back of our mind this n to the negative 2/3, which is valid for unimodal and monotone. So now I'm going to add something to it, right? I do not know the right ordering. If I knew the right ordering of my matrix, if there was no underlying permutation, I would just do this on each column and I wouldn't care. There would be nothing to pull across columns. What I'm going to do is I'm going to try to use the fact that I have a bunch of columns to try to aggregate the information across the columns to recover the right permutation. So the thing I'm interested in is the least squares estimator. That's the thing that basically says, well, among all matrices that have, say, monotone columns after permutation, which one is the one that fits the most to my data, right? That's the stupidest thing you could do. And the performance measure is going to be the average squared error in reconstruction of the original matrix that I had. All right? Turns out that if you have monotone columns, and that's only what I'm going to talk about now, this also implies some result about recovering the permutation and also recovering the matrix A itself, not the permutation of the matrix. So what are the rates? Well, they're a bit of a mouthful, but there's basically two terms that you can actually identify with me. The first one here is this n to the negative 2/3 up to some logs and things that characterize the complexity. But this is the thing that you would have even if I promised to you the permutation is the identity. The matrix is already sorted for you. Up to the log terms, this is what you would get. The second term is the price to pay for estimating a permutation. The usual statistical rule of thumb is log of the number of candidates divided by sample size. How many permutations? Well, n factorial. Sample size is n times m, the number of entries. So it's kind of an expected thing that you would see log n over m. But what's nice is that here you really have those two terms that decouple perfectly. And when the number of columns goes to infinity, the second term vanishes. So you actually have no price to pay for estimating the permutation, and you go back to having your original problem as if the matrix was originally sorted. So this is optimal up to the first log term. The second one, of course, is important, right? I don't want to remove the second term that came from the log n factorial. And as I said, as n goes to infinity, you recover the one-dimensional terms. And you can do this for unimodal, and you would get exactly the same bound. OK. So the question is, how do I do this, right? I promised to you an estimator, which was least squares, which was projecting among all permutations, right? I have somehow to minimize overall permutation, and this is an extremely hard problem. This is the so-called quadratic assignment problem. And if once I know the matrix, the permutation, it's fine. There's some algorithms like pulling adjacent violators algorithm, which is a well-known algorithm and runs pretty fast. But this quadratic assignment problem is something which is basically one of the hardest problems. It encodes several NP-hard problems. And one simple alternative is to say, well, if my rows are sorted, then when I sum each row, then I should still have some noisy version of a sorted vector. So maybe I could do this stupid thing, which is sum all the columns and then sort the vector that you get, and this is what you have here. So y times 1 sums the columns, quick sort orders them, and then you just say, well, this gives me some estimator for what the permutation is, and then I project. So since there's a lot of branding going on in statistics and data science, I decided to call this thing sausage. All right, and it's trademarked, so you cannot really call anything sausage anymore. And so let's talk about the sausage estimator. It's never too early to show pictures of sausage. And so it turns out this thing does not work. And the problem is that when I start summing all my rows, I have so much noise that starts to accumulate that it will always make some mistake. And for this very simple matrix, which is very sparse, right? There's only signal in the first column. The first column is going to accumulate the noise of all the other columns. And essentially, this thing is going to make a pretty bad mistake. Essentially, your error per entry is going to be over 1, meaning you're not learning anything. You could just spit out 0, and it would do the same job. So what we did is we improved it a little bit using some technique called rank score, which is just rather than summing, you actually take your entire row and you compare your rows in a smarter fashion, and you build some ordering of your rows. And so it's a bit of a mouthful, so I'm not going to detail it, but rank score does a better job. So what rank score depends on now, right? So if you look at this, without this part, this is the optimal rate that I described. And there's this quantity R of A star. If it was of order 1, then we would be back to the minimax rate. But this thing ranges between 1 in nice cases and square root of m in bad cases. It's close to 1 if the difference between two rows is either sparse or dense. All right? So this is actually nice. All right, so now if I look at the worst case that I get, I still have something that converges, but it's slower. The 1 over m that I had for the price to estimate the permutation becomes 1 over square root of m, which is slower. And so this points to something that I really like, which are called statistical and computational gaps. So I'm running out of time, so you know, as usual, simulations show that sausage does not work. By the way, in the paper it's called ranksum, because I'm not going to talk about sausages in academic papers. But essentially, you can find some example in which sausage completely fails. You can find some example in which everybody fails. But in the end, things are doing okay. So just let me sum up. So the results that I showed you were optimal rates for monotone and unimodal seriation. Those were used as a benchmark to understand efficient methods. And rank score was an efficient, but turns out to be suboptimal procedure. Does not go as well as the efficient methods. And there's a bunch of open problems that are attached to this. So we saw that the spectral method, actually you didn't see, but the spectral method is actually very competitive in simulations. And that's the method that that does not appear to be robust to noise, but seem to work pretty well. And there's some SDP approaches you can come up with. There's something called the TV denoiser, which is something that is good at approximating things that are well approximated by piecewise constant signals, which is the case of monotone and unimodal. Should work pretty well and be implementable well. And what I want to conclude on is this note about average case quadratic assignment problem, right? So quadratic assignment problem so I found this survey on the quadratic assignment problem that starts by saying the quadratic assignment problem, one of the most difficult problems in the NP hard class, right? This is basically encompassing everything you can think of. And it's a very, very hard problem. The source of hardness is searching through permutations. There's not even 2 to the n permutations. There's like n to the n permutations. There's even more. This is a very hard combinatorial problem. And we've had some success, partial success into understanding how average case can help understanding those things. But in a way, we did not really come up with anything particularly smart that's intrinsic to permutations, right? We just said, let's just reduce it to a one-dimensional vector and sort it somehow. And that's what rank score did, and that's what sausage did. We just did it in a smarter way with rank score. But I think this is the next boundary of what we're trying to understand. We know how to realize case sets, for example, right? Sparsity, case sparse things. We know we have to use our one norm. We know how to do that in a slightly more complicated way with cycliques and things like this. We have some natural SDPs. But there's really nothing that's intrinsic to relaxing the hardness of permutations. And I think all these average case problems or coming up with different average case problems, for example, statistical seriation, is a good way to actually attack those problems and try to say other things such as, other than, well, it's NP hard and I cannot do anything. Thank you for your attention.
Thank you very much. And unfortunately, great talk, but we are out of time so I'll push all the questions offline and invite Guy Bresler for the next talk.
Question while I set up the.
I'm sorry?
Maybe someone can ask one question while I set up.
Maybe you can.
Use mine. I screwed
Okay, so we're switching computers. Well, good idea indeed. While we're preparing the next
any
talk.
yes, no question?
Any yes, no, any questions? Have people looked at the quadratic assignment and the random instances?
Well, this is a random instance. It turns out that
But is so to repeat
a fully random instance, right?
repeat my question?
Yeah, so have people looked at the quadratic assignment problem in random instances? So the quadratic assignment problem is characterized by 2 matrices, and if you take them at random, I don't think it's going to make your life much easier. Those problems tend to be easier if you have some signal embedded in some noise and you're trying to recover it, and that's like, you know, playing click style, rather than just trying to find a click in a random graph. It's just harder, right? So I don't think randomness really helps you. It doesn't bring any structure that could help you.
So blended click is a special case?
No, plain click is not.
It's not.
I mean, no, not in average case. Not in average case. I don't think there's a nice reduction.